This video is about similarity, congruence, and proof. In the first problem, they give us this proof with all the statements and reasons except there's one reason missing. So we just need to figure out how they got from step 1 to step 2, because that'll be the answer to the question. Now step 1 is just the given, so let's fill in all the given and see what we've got. The measure of angle H is 30 degrees. So this angle right here is 30 degrees. The measure of angle J is 50 degrees. So this angle is 50 degrees. The measure of angle P is 50 degrees. So this angle is 50 degrees. And the measure of angle N is 100 degrees. So this is 100 degrees. So that's all the given. They're attempting to prove that these two triangles are similar to each other, which would mean that all of the angles are congruent. But we don't need to worry about that right now. We just need to worry about how they got step 2. H plus J plus K is equal to 180. Let's see. H plus J plus K is equal to 180. Well, we didn't really even need the given in order to make that statement. That's just a fact. All of the angles inside of a triangle always add up to 180. So of course H plus J plus K add up to 180. Alright, so I'm going to look at the reasons, but I'm looking for some kind of a postulate about the sum of the angles in a triangle. CPCTC, that stands for corresponding parts of congruent triangles are congruent. That's not going to be it. These triangles are not even congruent. Even in the end, we won't have proved them congruent. They're only similar. So corresponding parts of congruent triangles congruent, that doesn't make sense. The definition of supplementary angles, that doesn't make sense either, because we don't know that these angles are supplementary. There's no, if we were given that all of the angles are supplementary and then they said they added up to 180, that would be the definition of supplementary. Triangle parts relationship theorem. That doesn't sound familiar. That sounds made up. I'll come back to that one. Triangle angle sum theorem. That sounds familiar. Alright, so I'm pretty sure if you study your notes, which I'm sure you've taken, somewhere you have written down the triangle angle sum theorem, which says that the sum of the angles in a triangle add up to 180. So I think this is the answer. Alright, so this is the part where you take notes that maybe you didn't take the first time. So on a piece of paper, write this down. The triangle sum theorem. The sum of the angles in a triangle add up to 180. Write that down. Next time it comes up, you'll get the right answer. Alright, in the next problem, which concept can be used to prove that the diagonals of a parallelogram bisect each other? To answer this question, you need to know what it means for two things to bisect each other. Bisect means to cut exactly in half. So these are the diagonals of this parallelogram, and they're saying we want to prove that these diagonals bisect each other. That means they would cut each other exactly in half. Meaning, let's say this might turn out to be 5 and 5, like these two pieces would be equal. And maybe the other one would turn out to be 6 and 6. Alright, this one would be longer. But if these were the numbers, and I just made these up, this would be an example of the diagonals bisecting each other. The two parts on equal sides, on either side of the intersection point are equal. So let me skip down to these two. Similar triangles, similar rectangles. When shapes are similar, they do not have to be the same size. I can have a small one and a big one. All right? These two triangles could be similar. If you're trying to prove that two lengths are equal, it doesn't help if you have a small triangle and a big triangle. It would only help if you had if the two triangles were the same. You want them to be congruent. That would prove that the two sides are equal. Similar is not good enough. So, and either of these that say similar cannot possibly be the answer. All right? We want the sides to be equal, and for that you need congruent shapes. So it's either congruent triangles or congruent rectangles. Look at this picture. Do you see triangles in this picture, or do you see rectangles in this picture? I'm hoping you said triangles, because there are no rectangles in this picture. So for example, if we could prove that this triangle was congruent to this triangle, okay, then these sides would be congruent to each other because corresponding parts of congruent triangles are congruent. And these sides would be congruent to each other for the same reason. But you need congruent triangles to do that. So this is going to be the answer right here. Oh, whoops, I just put a box around rectangles. Can't be rectangles. There are no rectangles. Even the whole shape is a parallelogram. It's not a rectangle. It has to be this first answer, congruent triangles. Juanita is cutting a piece of construction paper in the shape of a parallelogram. All right, sounds like we need to draw ourselves a parallelogram. Two opposite sides of the parallelogram have lengths this and this. Okay, so two opposite sides. So let's say this is the 5n minus 6 centimeters, and let's say that this is the 3n minus 2 centimeters. A third side has measure 2n plus 3 centimeters. All right, what are the lengths of the two adjacent sides of the parallelogram? So first of all, let's find the length of all of these sides. How are we going to do that? Well, the opposite sides of a parallelogram are equal. So that means the 3n minus 2 must equal the 5n minus 6. So these two must be equal so we can make an equation. Let's solve this equation for n. Subtract 3n from both sides. That's 2n minus 6 is equal to negative 2. Add 6 to both sides. That's going to give us 2n is equal to 4. Divide both sides by 2. And that gives us n is equal to 2. Okay, great. Now we know the value of n. But what we really want to know is, what are the lengths of the sides? So to find the length of this side, for example, I need to take n equals 2 and I need to substitute it back in right there. So 3n minus 2 becomes 3 times 2 minus 2. So that's 6 minus 2, so that's 4. So this side has length 4. Do I need to take this and substitute it back in this one up to find out how long this side is? No, these are opposite sides, so this is also 4. Now let's figure out what this side is. Well, this side has length 2n plus 3. Again, we know that n is 2, so we can substitute that in. So that'll be 2 times 2 plus 3, or 4 plus 3, or 7. Okay, so this is 7. Alright, so my drawing turned out not to be to scale. I made it look like this side is longer, but really this side is longer, but whatever. It's a diagram. It's a schematic. Drawing, not to scale. Anyway, so I have these side lengths, which also means that this side over here will also be 7, because opposite sides of a parallelogram. Anyway, to answer the question, you need to know one more thing. You need to know what the word adjacent means. Adjacent sides are two sides that are touching. Adjacent means right next to each other. Your house is adjacent to the house of your next door neighbor. So, for example, these two sides are adjacent sides, 4 and 7. Okay? Or these two sides are adjacent, 4 and 7. Or these two sides are adjacent, 4 and 7. If you pick any two sides that are right next to each other, you're looking at a 4 and a 7. So that's going to be the answer right there. Okay, there are a few different ways to prove that two triangles are similar to each other. And one of those ways is called side-side-side similarity theorem. That's what these three S's stand for. Now, when you're talking about similar triangles, obviously the sides themselves are not equal. For example, this side right here is not equal length to this side. They're not congruent. But instead, what we're saying is that the sides are proportional, which means that if you take two corresponding sides and make a fraction out of them, the fractions for all three pairs will be equal. So let's see what we have. AB over XY. So that means that AB and XY must be corresponding sides. So you make a fraction out of them, and you get a number, which, by the way, this equals 2. So that's one pair of corresponding sides. For the side-side-side similarity theorem, we need 3 pairs of corresponding sides. So far we've got 1. And then there's this missing step right here. But let's see what the next step is. AC over XZ. So they're saying AC and XZ are corresponding sides. So you make a fraction out of them, the big one over the small one, just like before, which, by the way, also equals 2. And there you go. So now we have 2 pairs of corresponding sides. So we have a side, and a side. So since we're doing the side-side-side similarity theorem, the thing that must be missing, the statement that's missing right here, is one more pair of sides. So the missing statement must be what I'm about to draw in green. And we're doing big over small. So these are the only remaining sides, so they must be corresponding. So it would have to be BC over YZ. Alright, or it could be CB or ZY, as long as the letters are the same. And that has to equal something, sorry, it has to equal something that equals 2. It's going to be something that equals 2. Alright, I don't care what the numbers are, but they better equal 2. Okay, so let's see what we get. So I'm going to look down. So first of all, I'm looking for BC over YZ. Okay, this has the BC and the YZ, but it's upside down. So that's no good. This is not even close. These are angles, right? It's side, side, side. It doesn't say anything about angles, so I can forget about the angles. So it must be this one. So just like we predicted, it's BC over YZ, just like we thought, and it equals, and I was just looking for something that equals 2, and 6 over 3 does equal 2 like all of the others. So boom, this is definitely the answer. Alright, let's just do one more problem for this video. Which best explains whether or not all isosceles triangles are similar? Okay, let's think about that before we even look at the choices. First of all, you have to know what an isosceles triangle is. An isosceles triangle is just a triangle that has two equal sides, like this and like this. So for example, let's say this is a 6 and this is a 6 and this is a 4. That would make this an isosceles triangle. Okay, now when you have similar triangles, the sides do not have to be congruent, but all of the angles have to be congruent between the similar triangles. So let's say if I had another similar triangle that was like this. Okay, and so this will be isosceles. Let's see, I'm just going to double everything. So let's say this is going to be 12 and 12 and 8. These would be similar triangles. But here's the thing. This angle, well, okay, this is isosceles, so these two angles are equal to each other. But they will also equal these two angles, all right? The angles of the smaller triangle and the angles of the bigger triangle have to be the same. And see this angle here at the top? This angle would always also have to be the same. So, similar triangles have all the same angles, all right? The corresponding angles are congruent, even though the side lengths are different. Okay, so are all isosceles triangles similar? No, all isosceles triangles are not similar, because look at this isosceles triangle. Now, here's another isosceles triangle that I'm going to give it the same length here at the bottom, alright, just like the last one. Now, these are both side length 6. I'm going to double these, but I didn't double this one. Okay, so if I double these, all of a sudden, these are going to be 12, right? Boom. So this is 12, and this is 12. So these are not similar, because if they were similar, if I am doubling things, all of the sides would be double. Alright, so these would be 12, and if these were similar, this would be 8, right? Because I would have to double everything. But it's not. So it's still isosceles though. So these are isosceles triangles that are not similar. Just because it's isosceles does not mean that it's similar. Okay? So we could say that the side lengths are not proportional, because I will not get the same ratio if I match these up. If I do the 6 and the 12, for example, that's 1/2. But if I do the 4 and the 4, okay, that's 1. So I don't get the same ratio, so they're not proportional. Also, remember how I said the angles all have to be the same? For example, this angle right here will not be the same as this angle right here. Womp womp. Alright, the bottom is the same, but the top is much higher, which means that this angle is going to be skinnier. So these angles are not the same. Anyway, let's look through and see if we can recognize any of the thought process that we just did. Okay, first of all, we decided that all isosceles triangles are not similar. Not all isosceles triangles are similar. So if any of these statements say that all isosceles triangles are similar, that's definitely wrong. So all isosceles triangles are similar. So boom, that's wrong immediately. I don't have to read any further. All isosceles triangles are similar. Boom. I already know that's false. Okay, so it's got to be one of these two. All isosceles triangles are not similar because the pair of congruent angles within one triangle is not necessarily congruent to the pair of congruent triangles in the other triangle. Well, that's true. Alright, like these congruent angles down here will not necessarily be the same as these angles over here. So I'm going to come back to that. That's possible. That this is a possible answer. Let's look at the final choice though. All isosceles triangles are not similar. Given only one vertex angle of an isosceles triangle, there is not enough information to determine the measure of the base angles. Therefore, it is not possible to determine if the base angles of one isosceles triangle are congruent to the base angles of another. Alright, focus your eyes on this part right here. Given one vertex, there is not enough information to determine the measure of the base angles. Well, that's not true. And I can show you right now. So, if we know this is isosceles, and let's say I tell you that the vertex angle, alright, it says given only the vertex angle, so I'm just going to give you only the vertex angle, that let's say it's 80. They're saying there's not enough information to determine the measures of the base angles. Well, can we determine the measures of the base angles? Yes, we can. We know because of the triangle angle sum theorem, all of these angles have to add up to 180. So there's 80 right there. That leaves 100 left for the other two. And the base angles have to be equal. So if there's 100 left and it has to be equal, that means it has to be 50 and 50. So we could figure out the base angles as long as we were given the vertex angle. So when they said given only the vertex angle, there's not enough information to determine the base angles, that's false. We can. It is enough information. So that is not a valid statement. So that means this is the only valid answer. Alright, it's the only one of the things listed that are just not blatantly false. And there you go.